All right, welcome everybody to the February 2026 meeting of the Mornington Peninsula Astronomical Society. And as usual, I'll start off with a few things that have occurred in the last month or so. So you see up here in the top left the image from Mars from the Perseverance rover, and showing there are 10 of the samples that have been taken for later collection. Unfortunately, the US Senate voted last month to end the Mars sample return mission, which was due to go and pick them all up and come back. So far that they've taken 33 samples, and I think they plan to take 43 before the end of the mission, and they run out of sample tubes. It was a bit of a compromise apparently. The US Senate decided to stop that because what had been proposed by the US government was to cut NASA in half. Basically cut all funding in half, which would have effectively stopped any new projects in their tracks indefinitely, and would have put others into suspension. So this one was considered to be a risky one. Now China's not slow off the mark. They've jumped in with their own Tianwen 3 mission, which is going to be launched in 2028 and is due to bring back their own samples by 2031. So as things stand at the moment, it looks like the Chinese will well and truly beat the Americans to Mars to pick up their own samples. They won't go and take those sample tubes that are sitting up there, because that may provoke some sort of diplomatic incident, I imagine, if they did. But anyway, we may or may not get those samples back. Move over to the one in the middle at the top there. Two proposals are now before the FCC in the US, the regulatory body that looks after launches. One is by the company Reflect Orbital, which proposes putting 4,000 54-metre mirrors into orbit, low Earth orbit around the Earth, to reflect sunlight down to the Earth's surface at all times, and it will be the equivalent of 4 full moons in the sky. So if any of you are into astrophotography, I suggest enjoy it in the next couple of years, because if they get approval in the US, and the chances are under the current government there, the regulations may may be waived for them to go ahead and put this into place. Timeline for that is it operational by 2030. So in other words, it would be creating almost like a twilight all the time. Yeah, yes, Sylvie?
What would be the purpose of that?
The thing is, what would be the purpose of it? What it is to try and give solar energy 24 hours operation. So not just the normal day-night cycle, or at least that's the business case that's been put forward. So that's one of the brilliant ideas that is being considered by the current US government. And the other one is SpaceX has suggested putting 1 million small satellites into low Earth orbit, which is from taken to be from about just above the height of the International Space Station up to about 2,000 kilometres above the Earth's surface, to act as AI data centres. So in other words, looking to find a very cheap way of running AI powered by sunlight 24 hours a day and talking to each other via optical lasers. Again, the proposal for that one is by 2030, and also seeking regulatory waivers so they can make that. Now, as you can imagine, 1 million satellites in the sky, you've seen what Starlink is like, and that's barely several thousand. So can you imagine what 1 million is going to be like in the sky? So if these go ahead, you could pretty much forget astrophotography really from that point forward. Over in the top right hand side there, shown is an Electron rocket about to be launched from the North Island of New Zealand. New Zealand has announced that they've raised their launch cap from 100 rockets a year, which is their current limit, up to 1,000 per year, because they've already exceeded it. Most of these launches you never get to hear about. If it goes on the track record to date from their launches, it's going to be worth about $20 billion to their economy. So huge effort. And so New Zealand's on target soon to put up 1,000 a year, whereas Australia, well, how many did we put up last year? 1? Yeah, so we got quite a way to go. So New Zealand is currently the number 3 country in the world for putting launches into orbit. So pretty amazing, and that's from the Rocket Lab company shown there. Down in the bottom left-hand side, the rotating asteroid there, the asteroid Bennu, which in 2018 was visited by the OSIRIS-REx mission, which landed on the surface, took a big sample, and over the next couple of years brought it back to Earth for analysis. It has had very recent analysis done, and they've detected amino acids, glycine and alanine in it, which are, of course, are precursors for life. So in other words, it's showing that life could originate even before water was present in the solar system. So the mechanism that they're suggesting is that it comes from ices, not necessarily only water ice, under radiation in the outer reaches of the solar system at an early stage with that one. So that is very interesting. And on the right-hand side there, University of Trento has been looking at old Magellan data. That was a spacecraft that visited Venus and did radar mapping way back in the 1990s, but they've applied more sophisticated techniques to the radar data, and they're pretty convinced that they've detected lava tubes underground, up to 45 kilometres long, 1 kilometre in diameter, so in other words like underground caves in Venus, with a thickness of the roof of 150 metres. Now lava tubes occur on Earth, Mars and the Moon as well, and so they've now been confirmed on Venus, though I can't see too many people going to live on Venus in the near future, I would think, even inside one of those lava tubes. All right, so tonight, welcome, and welcome to any new members. Unfortunately, I don't have the list of new members here tonight. Are there any people who've joined in the last month or so here tonight? Yeah, welcome to the Society. Feel free during the break a little bit later to get up and approach any of the committee members who I'll ask to put their hand in the air so you know who they are. Yeah, there we are. And there's one down here as well who doesn't have his hand in the air. So welcome to the Society, and if you have any questions, please do ask. I'll go through the events the past month and the upcoming month, and then I think Chris is going to be a little bit late tonight, so we might bump the monthly photo challenge until after Sky for the Month. So I'll then hand to Guido, and then Eden will talk about James Webb Space Telescope related changes there, things that have occurred, which should be very interesting, given that the James Webb Space Telescope is about halfway through its life already. So it's hard to believe it's been up there at the Lagrange point that long. Then we'll have a brief 7-minute look at Clouds 101 from the NASA Goddard Space Flight Center, and also what lies in the Moon's permanently shadowed craters. Now this one's given by the chief scientist of NASA at the time, who's now retired since giving this talk. That goes for about 15 minutes. And then we'll close by looking at the Polaris Dawn mission, which was the first commercial mission that put 4 astronauts into an elliptical orbit. So they went from higher than the International Space Station out to about 1,400 kilometres above the Earth's surface, flying through the Van Allen belt. And the Van Allen belt was one of those areas of radiation around the Earth that was a concern during the Apollo missions as the Apollo astronauts travelled through it on transit, whereas they looped through it a couple of times over that 5-day mission. All right, so recent events here. Shown in the background there is the MPAS marquee set up at Frankston waterfront recently. That was on the 7th of February. Since we last met on the 24th of January, we had to call off the members' night and the barbecue due to a total fire ban and high fire danger at that time. So that's one of the few times that we have called off one of those. 28th of January, we had a committee meeting that talked about a few things. EMP means Emergency Management Plan. We didn't let off any nuclear weapons, and it was electromagnetic pulse. It is actually an Emergency Management Plan. We also looked at upcoming events, such as preparing for the Waterfront Festival and the subsequent gatherings as well. It's also time to remind members that if you haven't renewed for the year yet and you're due to renew, you're overdue, so please go ahead and do it. And we also talked about or prepared the plaque that went on the small dome out there, given that it was donated to the Society. 31st January, we had the Cosmology Discovery Group here on that Saturday afternoon. Followed on the 6th February by the public night, where fortunately Trevor had no cloud that night, and 81 people turned up for that one. 7th of February was the Frankston Water Festival. The estimate was about 40,000 people attended in total, but where we were placed was away from the centre of things, which is just as well, because Chris's estimate of about 1,000 visiting during the day, you just would not have coped with 40,000 visitors coming and sticking their nose in the tent and wanting to hold the meteorite and have a look through telescopes. The week later, on the Friday 13th of February, Tim Patson was here giving his Indigenous astronomy talk, and again he was lucky not to be encumbered by a cloud. And on Saturday the 14th of February we had the Trivia Stargazing concert here, another one of those with the Cranbo Lions concert band, and they were very lucky. Weather was not too hot, not too cold, and clear skies, and they had a good attendance there of about 120 people. So coming up soon, this coming Saturday, I assume the Working Bee and barbecue at the Briars will go ahead this time, unless we somehow get another severe total fire ban. 24th of February next week, we've got Rye Beach Probus Club will be coming here, 49 people expected for that one. Committee meeting will be the following night and on Zoom, so members are welcome to dial into that and listen if they wish. 26th of February, we've got St Mary's College, St Kilda again. Apparently Year 8 is the old Year 9s. Year 9s used to be a horror year for teachers, and apparently they're maturing earlier these days, and it tends to be Year 8. So we've got 70 Year 8s. It's still horrible. 4th of March, we've got Parkdale Secondary College again. We get those every year. About 120 Year 7s expected for that one, up at the school in Mordialloc East. And we're set up the telescopes again in the small park right next to the school on the southern side of it. 6th of March, we've got the public night here, and Manfred's giving the talk for that one. And the next Cosmology Discovery Group is on the 14th of March, followed by the next of these meetings on the 18th of March. Then the Society's got a couple of events in the next planning horizon. A couple of days down at Inverloch for a couple of members are going down there for their Equinox Festival. They've asked for a couple of telescopes, so we've got enough telescopes for that in conjunction with the Latrobe Valley Astronomical Society and the tourist body. And that's a public night effectively down there. Overlapping on the same day, on the 21st of March, we got the Telescope Learning Day here at the Briars. We do 2 of those every year, and this is the first one for 2026. And so far we've got 25 people booked for that one.
First MOFO for 2026, and surprise, surprise, we've got the moon. We've got a lunar eclipse coming up on the 3rd of March. Full moon, blood moon. Blood because it turns red. A couple of other... So yeah, for the uninitiated, Astro MOFO is a monthly photo challenge where members are tasked with capturing an image of the topic of the month. The images are then collated by me and they are presented at the next member meeting. Now this one being the moon, a couple of key dates for the moon. We've got the new moon, which was yesterday on the 17th of Feb. First quarter moon is on the 24th. The full blood moon will be on the 3rd of March, and the last quarter moon will be on the 11th. And these are all different phases of the moon that you can photograph and get images of different features with different shadows cast in different directions, making for really interesting photos. And what we have in the background here is a few days after the new moon with a crescent image of it. So with the blood moon, 3rd of March, we have the lunar eclipse. It also coincides with the full moon. And what I'm proposing to do that day, I'll be here at MPAS from around about 7:30 onwards to observe and photograph the lunar eclipse, and anybody else, any other member who wishes to attend is welcome to come on that date as well. And bring your gear, bring your cameras, tripods, whatever you like, and we'll make a bit of a day of it. The main phases that the moon goes through during the lunar eclipse, and on the 3rd of March, the eclipse begins at around about 7:48. So by the time the moon rises, it's already started happening. The moon is already entering the Earth's penumbra, which is the minor shadow of the Earth, and that has already started happening by the time the moon rises. The moon will go into the Earth's umbra, and totality will be from around about 10 past 10 p.m. and it will last till around about 11:04 p.m. And that is the phase where the moon is completely in Earth's shadow, and it turns red because the only light that gets to the moon is the red light that is refracted through the Earth's atmosphere. So if you picture watching a sunset and the glow on the horizon is usually red during the sunset, that's because the red light is refracted, the rest of the light is scattered, and effectively what is happening is all of the Earth's sunsets all at once are all focused on the moon, hence we get a blood moon. And the moon clears the Earth's penumbra again by about 1:26 a.m. Now from the time when the moon's entering the penumbra and when it's going through it, you might not notice much of a difference visually, but when it does start entering the umbra, which is the main shadow of the Earth, that's when you do start seeing it darken significantly and start turning red. These photos here, by the way, are from the 2022 lunar eclipse and were taken here at Briars as well. Okay, this little animation shows you pretty much the timing of everything from when the moon starts rising and as it goes through the eclipse. So if we play this is it coming up above the horizon and entering the Earth's penumbra, which is the outer shadow of the Earth. Then at around about just after 9 o'clock, it starts going into the umbra, and then by about 10 past 10, as we see here, it's completely in the Earth's shadow. That lasts for quite a while. It's quite a long eclipse because it's travelling through a fair part of the Earth's shadow. Starts clearing it just after about 11:15. Clear of the umbra by about 20 past 12. And then it starts clearing the penumbra, and we are left with a beautiful, clear, full moon by around about 1:30 a.m. So if anybody wants to stay that long, you're more than welcome. I'm not sure if I will, but we'll see how we go. Okay, so the challenge is to capture the moon at different phases using also, you can use different equipment. You can use a camera lens or a telescope. Barlows on your telescope will also help give you increased magnification to focus on specific craters or specific ranges on the moon. And they can also help you get nice shadowing effects during the leading through the first quarter and the last quarter of the moon. You don't get too many shadows on the moon during the full moon unless you're looking at the edges of it. So the challenge is try and image areas of interest. You might want to try and image under higher magnification the Apollo landing sites or other significant craters. And another thing that we can do is also, when you're photographing high resolution images of the moon, rather than shooting individual frames, you shoot video, raw video formats, and then there's a process whereby you can extract the frames from the video, stack those frames and get a much sharper image than what you would normally get from just a single shot. And that's an example over there as well of doing that. You're also able to get more contrast. You're also able to get a bit more color as well. So you're able to see the more exposure that you get on it, the more frames you're able to bring out more color that exists on the moon as well. Okay, so the other thing I wanted to mention was AstroMOFA. We're going to have a winner this year. So we're going to have a definite winner, which will be by popular selection. The winning photograph from all the AstroMOFA challenges this year, it'll be by popular vote, so no judges, but everyone will be able to vote on them, and we'll have a popular winner. That popular winner will end up being our cover for the 2027 MPAS calendar. And watch this space because I'm working on a few other things as well. We'll see if we can maybe work out some prizes or something for different types of images. So Quite a bit will be happening. We'll also be doing a few more workshops this year to help people with their processing and that sort of thing, so just keep an ear out for that. I'll be posting information about that on the socials as well. Any questions? Easy. Covered everything. Thank you all very much. Back to Peter.
Chris, one question.
Yes.
How long would you take it to do?
A few minutes will usually give you a good result. Obviously, seeing is another thing that you want to be aware of, and if your video, when you're doing it, it's very blurry and hazy, it's probably not going to end up being the best. You also want to be aware of that. But a few minutes, but people take a lot of video, and the benefit of doing that is that you can, the more video you have, then you can reject a lot of frames and only really keep the best quality frames in that video to stack for your image. So usually when you do collect, you might collect 20 or 30,000 frames, but you might only choose to stack a couple of hundred of them, of the best ones of those, to give you the clearest image. So, yeah.
Pick your eyes out.
Sorry?
Pick your eyes out.
Yep, exactly. Well, there's algorithms and software that does that all for us, so we don't have to go through 3,000 frames and individually look at them and assess them. But yeah, it's there's different software that we can use to do all of that, and I'm happy to go through it. I'll do a bit of a workshop on that soon to show us how to do it. But also, if you go back through the eScorpius editions, Russell Smith has done an article on one of the eScorpius about doing planetary imaging and using that software and how to do it. So I might actually I post that link regularly because it's a really good write-up in the newsletter on how to do that. So I'll post that link in our eScorpius group. Thank you.
Okay, so sky for the month for the rest of February and the first half of March. Having a look at the solar system from the top. Let me just grab my laser pointer here. So we can see well, the sun in the middle there, Earth around here at the moment. You can already see that Mercury and Venus are very close to the sun from our point of view, and Mars is basically hiding behind the sun. So that's what it's going to be like for the next month or so. And then if we zoom out from here to the outer planets, as you can see, Jupiter is kind of in the same place as the Earth there, right? So away from the sun. So we will see that in the all-sky view later, that Jupiter is in a great place to observe at the moment, while Saturn and Neptune are also kind of almost lost to the sun's brightness now. So they're very close to the sun, and you can only observe them right before sunset. Okay, just zooming back in and then having a look at the next couple of weeks. I'm not sure. Okay, there we are. So zooming back into the inner solar system and then fast forwarding through the next 3 or 4 weeks, we can see that Mercury will pass in between the sun and the Earth. So that's the inferior conjunction. And Venus will kind of come back from behind the sun there, while Mars basically stays hidden for the next few weeks. All right, what does that look like from the Briars? So this is the view for the 1st of March, around 7:30 p.m. So that's close to sunset there. So the sun will set around 8 p.m. on the 1st of March. And we have the equinox coming up on the 21st of March, so just after the next meeting. Venus now is an evening object. You could see it's still very close to the sun, but it'll basically come back from about mid-March, and then will be an evening object and observable. We have Saturn going into its conjunction with the sun on the 25th of March. So that means it'll be directly behind the sun from our point of view. It'll become a morning object from about early April. So if you get up early just before sunset, Saturn will come back from behind the sun, or we will kind of overtake. So we will be able to see it again in the early morning sky, and then it'll return. It'll start rising earlier and earlier until it becomes an evening object again towards September or October or so. Neptune is very close to Saturn at the moment, and because those two are not moving that quickly, it'll stay like that for the next few months. So it also has its conjunction with the sun on the 22nd of March. Right, another planet here in this view. So this is around 20 past 9. So you can see Jupiter there at the top there. So kind of in the north. And Jupiter, very bright, very easy to observe. We had some really nice views of Jupiter at the last couple of events here. So really a great time to have a look. It'll stay like that for the next couple of months. Uranus is pretty low in the northwest there, so but it's also still observable. And then the moon, I had to put that on this slide because it's right here in the picture. So we just had the new moon yesterday on the 17th. We'll have the next full moon on the 3rd of March, and we'll have a total lunar eclipse. And we'll hear a bit more about that from Chris later on. And then the next new moon on the 19th of March. Right, moving forward. So this is around 10 p.m. Just having a look at the brightest stars. So at the moment, you can see Orion extremely prominent. So the biggest constellation, or easiest to recognize in the sky. We have Sirius and Canopus there as the two, like the brightest and second brightest star in the sky. So that is basically with us all night at the moment. And the Southern Cross is a bit higher again in the sky around 10 p.m. than it was last month or the month before. So also very well placed for observation. And yeah, the main constellations really, we have Orion and Canis Major as kind of the summer constellations in the sky. And yeah, this is the Southern Cross there. Also, again, a bit higher than it was in the last few months. All right, if we then continue through the night, there's not much happening in terms of planets for the rest of the night. So it's really only Jupiter that's readily visible or observable at the moment. So this will take a little while until we get to the sunrise again. So you can see here 24P Schulmaz, that's a comet that's observable at the moment. And it's not very close to the sun from our point of view. So that is one of the comets I'll have on another slide a bit later. And then you can see there Mars rising just before sunrise, but it's basically too close to the sun to observe at the moment. And Mercury, it's close to its inferior conjunction and unobservable at the moment. Sunrise around 7 o'clock in the morning at the moment. So quick look at the apparent sizes of the planets. Jupiter, as I said, very bright, very, very big at the moment because we're very close to the planet in its orbit at the moment. Saturn moving away from us, so not as big anymore, and you can only observe it just before sunset. And yeah, you can see Venus and Mercury are also, well, Venus is pretty small visually compared to at its closest point in its orbit. So we're going to hear a bit more about the moon from Chris later. So I'm just thinking I might go through these slides anyway. So these are slides that I usually use at our astrophotography workshop or our telescope learning days sometimes. So just having a quick look at the moon. This is a photo from 2018 from a total lunar eclipse, or a series of photos from a total lunar eclipse where you can see kind of from the just brightly lit full moon all the way into the totality when you get this nice red glow. So hopefully we'll have like nice clear skies for the next lunar eclipse. So if we just look at the moon, it's 380,000 kilometers away from Earth. It's a quarter of the diameter of Earth and about half a degree of field of view in the sky. So it's like, I'm sure most of you have heard of the moon illusion, right? When it's very close to the horizon, it looks a lot bigger, but it really only is this half a degree or so in the sky. So if we look at the moon phases, so we have the full moon here when it's right behind the sun from our point of view, sorry, behind the Earth, opposite the sun, and then it goes through its phases. And what you can see is that it actually wobbles a bit, right, in its orbit. So we can see a little bit more than 50% of the surface because it always points the same side towards Earth, but because it wobbles a bit, we can see slightly more than 50%. And there we have new moon when it's between the sun and the Earth, which was yesterday, of course. And then coming out of that, we'll see the crescent now starting to reappear. Another nice photo that I always use from that Greg took. It's actually a composition of 3 independent images. So we have the full moon here, and then we have Jupiter here in the corner and Saturn here. It's quite faint, but maybe you can at least have a rough idea where that is. And this just shows the apparent sizes of the moon, Jupiter, and Saturn when viewed through the same telescope, like same focal length, same eyepiece. So you would, I don't know why this went so quickly. All right, the other thing I wanted to quickly mention is that yesterday was also the Lunar New Year, right? So Lunar New Year is celebrated in a lot of cultures, especially in Asia. So it's also called the Spring Festival or Chinese New Year. And from an astronomy point of view, it's interesting because it's the second new moon after the December solstice. So you can see that it's actually, it's a lunar phenomenon, right? It's the second new moon, but it's linked to the solar year, to the December solstice. And so this year, it was yesterday on the 17th of February, beginning of the year of the horse. This linking of the lunar calendar to the solar calendar is called a lunisolar calendar. I found that interesting to just see how that actually works. So a lunisolar calendar is where you take the lunar month, so that's exactly the time between 2 new moons or 2 full moons. Right, and that's 29 days, 12 hours, 44 minutes, and 2.9 seconds, apparently. So if you take 12 of those months, you don't get a full year. You only get 354 days, right? So if you just use the lunar calendar, the start of the year will basically shift compared to the solar year every year, right? So your new year will be a little bit earlier, 11 days earlier every year. And because that's a bit annoying, if your spring festival suddenly falls into winter, that doesn't really work, right? So the trick is the same trick we use for solar years. We insert not leap days, but leap months, right? So every 3 years or so, every 2 or 3 years, you have to insert another month to make up for that 11 days difference between the lunar month and then the 12 lunar months and the solar year. And this has been known since ancient times. So the Babylonians used the lunisolar calendar. The ancient Roman calendar was based on this principle. And the Chinese calendar, the Hebrew calendar, and the Hindu calendar are all based around that. And we still have things like that in Christian culture as well, right? Where Easter is linked to the full moon after the equinox, right? The northern spring equinox. And I think there's the link to the Hebrew calendar as well, right? So it's always trying to link the solar year to the lunar year. But some other calendars use purely lunar calendars, where that means that those festivals shift through the year every year. And so, for example, Ramadan is at a different time every year in the Muslim calendar because that's a pure lunar calendar, and that means that these festivals basically shift through the solar year every year. All right, so that's, and Chris is here, so he can talk more about the moon in a little bit. The other thing I just wanted to quickly mention is there's a lot of noise on social media at the moment about this great planetary parade or alignment on the 28th of February. And this one even appeared on nasa.gov. Maybe because it's not just completely made up. So there's a little bit of truth to it. So on the 28th of February, we will actually have 6 planets in the sky. So we'll have Venus here, Neptune and Saturn here, Uranus here, and Jupiter here, right? So all of those planets, well, plus the moon, actually, if you count that one as well, right? So they will all be in the sky at the same time. Now, I created this using Stellarium, right? Just setting it to that date, and then having a look at at all the things that are above the horizon there. But what I had to do in Stellarium to see this is to turn off the atmosphere simulation, because if you turn on the atmosphere simulation, it looks like this, right? So basically, everything up to Saturn will be basically invisible because it's too close to the sun, right? So this is just after sunset. Like a minute after sunset, you can see, well, those planets are technically above the horizon, but it'll be very, very difficult to spot them. I guess you can probably see Saturn and Neptune there just a little bit later, but I think Mercury and Venus will be very difficult. So Saturn will be around 6 degrees above the horizon at sunset, right? So you need a very clear view of the western horizon to see anything there. So I guess, I mean, with all these things, anything you see on social media, if it says something like once in a lifetime opportunity, it's probably not true. All right, a couple of comets. Again, only comets that are brighter than 10th magnitude. So we have C2024 E1 Wierkosz, apparently. That's close to the pronunciation. So named after a Polish astronomer. It's, I think, still around magnitude 6 to 7. And this is a comet on a very hyperbolic orbit. So it's its first visit to the inner solar system, and probably its only visit for a long, long time. It's in the southwest after sunset, but it's fading very quickly now. The second one is C2025 A6 Lemon. That one's around magnitude 9, also fading. That one is on an orbit that's around 1,300 years, so a bit more predictable. And that one is in the southeast and rising around midnight at the moment. And then we have 24P Chaumas, and that one is magnitude 9 at the moment. This is a Jupiter family comet on an 8-year orbit. So that one's coming around pretty often. It's low in the northeast, but as you saw in the all-sky view, it's rising around 2. I think it's rising a bit earlier now. So this might be wrong. I think it's rising around midnight or so. So those are the 3 comets that are currently visible. And then in terms of meteor showers, we have the Gamma Normids from the 25th of February to the 28th of March, with the peak around the 14th of March, but probably not a very promising event, and also affected by the full moon. All right, that's all. So the sources always Stellarium, NASA Eyes on the Solar System, the Astronomy Yearbook, which again you can download for free for 2026, and Wikipedia. Question, yes? Yeah.
Excuse my naivety, but when you say magnitude, is that kind of the visibility of it? Is that what that means?
Yes, so magnitude is a scale for how bright it is. Yeah, so magnitude 5 or 6 is probably the limit of what you can see naked eye. And Jupiter at the moment, for example, I think is magnitude -1 or something like that. So magnitude can go negative for something very bright. Yeah.
The smaller the number, the brighter it is.
Yes. Yes.
The other way. And it goes in steps of 2.5 times. Like it's not
That's the increments?
Yeah, the increments. So if you go from 1 to 2, it's 2.5 times fainter.
Yep.
And you go to third magnitude, it's another 2.5 times.
Yeah, that makes sense.
Another 2.5 times fainter.
Thank you.
Other questions? The lunar eclipse is on the 3rd of March.
About 10 o'clock at night, I think it is.
Chris has all the details for you in a minute.
I'm the coordinator of the Cosmology groups. I think I see quite a few familiar faces from our group and our new members up the back there. G'day, how you going? So I think tonight was really more about giving everyone a bit of an idea of how we're going, the Cosmology group. We've been going now, Peter, 5 years, a long time. I think we've pulled apart the subjects, placed them together. Prem is one of our members up the front there. I think we've covered pretty well everything. But this year we've decided to revisit the creation theory because such a lot of changes have occurred in the creation theory of the Big Bang. We're going to introduce new concepts. I'm going to introduce philosophy of the universe. This is a very big area. And Doug is one of our members and our regular speakers going to talk more about life elsewhere in the universe. There's so much going on in these areas. So this is our team of presenters. There's Brian Severs at the moment. Brian's suffering from terrible back problems, but I think we've got him back at our next meeting coming up. And Dr. Doug Days, he's one of the local GPs, just retired, but he's really taken on his job as one of our presenters so well. I'm very proud of the way Doug goes, and of course yours truly over the road. So Peter, I think I stood here maybe 2 years ago. Was it 2 years?
I think it was about 2020 or 2021.
Yeah, and I presented the subject of the reionisation of the universe. In other words, what happened during the first 1 billion years. Now, the classic theory of physics and all that sort of thing going on was that the fact that we had a very small, the classic theory is a very small singularity. The whole of the universe itself was squashed down into this atom, I suppose you could call it. And then from there on it was tickled by quantum fluctuations, if we could call them in physics, and next minute we have a universe within a half a second. And that universe, of course, has gone on to grow and grow bigger and bigger as time goes on. Now, during that early stage, and what's changed is that early universe was around about 2 trillion degrees, roughly. That's the estimate at this stage. And if you know much about physics, I think some of our members here are ex-physics teachers or current physics teachers. We know about if you have an ionised atom, basically the electron has been ripped apart from that atom, okay? Or it can, in some cases, can join back. That means that the existence of hydrogen and helium, which is really the biggest part of our universe, has not been able to actually coalesce together. They call it cold helium and hydrogen. So our original theory was that these early days of star formation and galaxy formation took really about 1 billion years to happen. Does that make sense? But things have changed significantly, and we'll move on from that. So what I wanted to talk about tonight is really the perspective of all that we were talking about. There's been a significant cosmology survey done in the US that I just happened to fall across only recently. We're going to learn about the universe and when it cooled down, and we'll learn about cosmology and astrophysics and how it's all changing rapidly. And we're going to learn about the consequences of this in the university training and their examinations. That's a very big problem at the moment. And one of the big things at the moment is anyone familiar with dark matter? You've heard of it. Put your hand up if you've heard of dark matter and dark energy. Yeah, so you've actually heard about it. Now, dark matter is under great question. Does it exist? That's something we'll talk about. And finally, we're going to say is what all these things we talk about in cosmology, are they being tested? So here's the USA result. There was a study done in 2023, and they asked people in a setting like this, why wouldn't you want to come on and learn about cosmology? Okay, and some of them said it seemed just too hard okay? I needed to know calculus. That's a difficult one. I get maths anxiety when I think about anything to do with maths. I don't feel I have the learning capability of this sort of technology. I think it is of no practical use to me. That's an interesting one. So in other words, they can't put together, is cosmology helping me in my life in any way? I miss doing science, physics at schooling. That's a relative one. Cognitive discomfort. In other words, if people thought it would hurt, that frightened me thinking that. It may give me information overload. Yep, that's fair enough. And there could be conflict in scripture-based accounts and general religious beliefs. In other words, some people did not agree with what we were teaching from a science base. None of this, ladies and gentlemen, none of this is needed in cosmology meetings. None of this. You just come along and listen and have an idea. Pram, when you started many years ago with us, didn't you? You're now writing to me with significantly complex subjects about creation, aren't you? And would you have done that 5 years ago?
Probably would have.
Okay, but that's where we are. You're writing to us and testing us and our knowledge, and again, the banter is fantastic. So I can only encourage people that want to join our group. You only have to need to contact Nerita. Do you know Nerita? And she'll put you on the mail list and just come along. So this guy up here, anyone know who he is? He's a very argumentative physicist. His name's Fritz Zwicky. And he was the guy that said there is such a thing called dark matter. In other words, dark matter is only active within a galaxy. In other words, it keeps everything from flying out. So as a galaxy, most galaxies do an anti-clockwise rotation. About 95% of mainstream galaxies do. And what stops the stars and the planets as they're rotating from flying out? Dark matter and gravity too. We must not forget gravity. So Fritz Zwicky came along and said dark matter's there and doing its job. So let's have a bit of a think about what we're doing in the quiz. Sorry about this. What changed the perspective of the early universe? Does anyone know? I'm giving it away what I'm saying here, but what changed the perspective? Since 2023. Sorry? Exactly. And what's James Webb done? What has the telescope done to us?
Show us the things that happened a lot earlier than we thought.
Yeah, that's the big thing. And what's happened is profound. So in other words, we have a model of the early universe starting, and we're talking about when stars and galaxies form. James Webb, the Hubble telescope did a good job of this, taking photographs, but it couldn't push its way through the cosmic microwave background to take these early photographs of the universe. And suddenly, since 2023, we're seeing galaxies, because galaxies come after star development, we're seeing galaxies actually developing within 250 million years just after the Big Bang. Now, in our world, that's profound. We never thought that this could all happen. We're seeing main sequence stars developing at 200 million years just after the Big Bang. So that in itself raises a huge amount of questions. One, what is then the real age of the universe? Number two, is the universe 13.792 billion years old? Is it older than that, given time that these galaxies need to develop over time? There's some of the questions. Can you explain the Hubble tension? Does anyone know what the Hubble tension is? You've heard of Mr. Hubble, Professor Hubble. He was the astronomer in 1929 at the Hubble telescope in Los Angeles. He trained as a lawyer originally and became a fantastic astronomer. Anyone know what the Hubble tension is? No?
It does the speeding up the expansion.
Exactly. It's about the expansion of the universe. We all know the universe is expanding, but now we have tension amongst corner groups of physicists and astronomers saying, hey, it's not expanding at 74 kilometres per hour per parsec. It's actually expanding at 69 kilometres per hour per parsec. Or another group is saying, no, it's expanding at 65 kilometres per hour per parsec. So what's happened is that they're all disagreeing on the velocity of the universe expanding, and they're all arguing about it, and it's caused a tension amongst the key people in cosmology. That's what the Hubble you're bang on right. It's all about the disagreement amongst the key people about how fast is this going at this stage. Does that make sense? Okay. What matter in our universe is now under question? We just talked about dark matter. I'll answer that question. Is our universe a balloon shape, a saddle shape, or is it flat? What's been talked about in the last few years? We actually live in a flat universe. We don't live in the universe where we're on a saddle and we go all the way around and we come back to where we are. We do when we look at the Earth and we come up over and we come back to the same point at the top. But in fact, we actually do live in a flat universe, and that's been found out through a huge amount of mathematics. I won't go into it. It's a big story, but in fact, we are living in a flat universe. Now, when we say a flat universe, does it have borders? We don't know, but we think the universe started at a particular point, but as it has grown out and increased in size, it's roughly about 95 billion light years out now at this stage. And this is the drawing of where we are here. So in other words, our universe from here, the observable universe, to some of the galaxies here is about 45 billion years. That's how far some of the new telescopes can see these days, which is remarkable. But the universe's edge, is what we call an edge here, is about 95 billion light years to this edge. Beyond that, there is no border. So you ask a cosmologist, say Brian Cox or Brian Green, saying, well, what's on the other side? Does anyone know what's on the other side of that border there? We don't know. We know it's space. That's all we can say at this stage. Does that make sense? That probably doesn't make sense. Because we're living in a borderless universe at this stage. Hypothetically, if the universe may be chaotic, okay, then how do we explain entropy? Does everyone know what entropy is? Right, so the universe started in order. See this chair here? This chair is in low entropy, okay? That means it looks like it's in order. It's sitting, it's strong, it's made of atoms, made of steel and iron compressed together. But in a billion years, I'll come back, what is that going to look like? Disorder, okay? So everything, you, me, this room, the stars, the galaxies, will start from order, low entropy, to disorder, high entropy as time goes on. We cannot change that in our universe, okay? It's one of the 26 constants of our universe. It's a law that we can't change. It's part of what they call the two laws of thermodynamics, the second law, okay? So when you leave Earth, just as a funny question, what happens to time? We're in a rocket ship, off we go. What happens to time? Sorry?
I guess it stops.
It'll stop if you reach the speed of light, okay? And you'll be stretched so much as if you were jumping from the event horizon into a black hole. You'll be stretched, or what we call spaghettified, okay? Stretched out because of the high gravitational forces in a black hole. And we can think of examples. If I put an atomic clock on here, and then we synchronise another atomic clock on the floor, and I come back the next day, will there be a difference in the times? Yes. They'll be minute to a point of 0.0000 right down, but there will be a difference. Another example was in NASA took two 747s. They put two atomic clocks in each 747. They synchronized them exactly together. One went around the Earth twice, clockwise. The other 747 went around the Earth clockwise. And they also had an atomic clock synchronized specifically on Earth. Guess what the differences were? There were significant differences, again 0.00, but the times were different. Another example would be if you take a child and they were born and they lived at sea level, okay, and you sent another child, the twin, to live on the top of Mount Everest, hypothetically. Which child is going to be, is the child, the difference in the children, there's going to be a difference in age and growth factor and all that? Will there be? Yeah.
We're rotating around Earth about, what, 1,600 kilometres an hour?
About 1,000 miles an hour.
Yep.
Yeah.
We're also orbiting the Sun.
The what?
We're also orbiting the Sun.
Yes.
About 30
the-
kilometres a second or something.
Yeah, it's pretty fast. Yeah.
The Sun's also orbiting the galaxy.
Yep.
So if you had a 0 point, like an unmoving one, we're moving about 2 million kilometres an hour. How much is our time actually slowed down because of that?
I don't know, but what I would go back to is Einstein's general theory of relativity. In other words, in 1915 he published that, and if you are your reference point of where you are at that particular second and moment of time.
If you stop moving,
Yeah.
the person sitting next to you was
Yeah.
going at that.
Yeah.
time
It would be a difference. Yeah.
So we're
Yeah.
actually slowing time down because of staying on Earth
Mm.
compared to a universal reference point.
Mm. Yeah. Have you got a question? Okay. The question was, where does the universe start and finish? Unfortunately, I'll give you another typical cosmology answer. There is no beginning. Well, there was a beginning in time, but there was no time before that. But the universe did not have a place or where it was when it started. There was no place and no time.
But isn't that been challenged even by our lack of confidence now that it actually started?
I'd love to know what the challenge is.
Well, the challenge would be that if it's older, how much older is it?
Well, yeah. And
Therefore, was there a beginning
yeah.
and all, or are we just observing something that we think was a beginning? All these things are starting to come into
Yeah.
question, aren't they?
You've come up with 2 or 3 different concepts, but the main concept to answer that was relativity is the most important thing to stand its ground, and it's been proven millions of times. But the question what you're talking about is that at the beginning of the universe, and there are 2 scenarios now we know of that could be the answers to the beginning or birth of the universe, or what we call the Big Bang, is that the questions now happening is what was before then? What state? Was there a state of a universe? Was there time? Or were we a birth child of another universe, albeit a multiverse, parallel universe, a mirrorverse? There's many different concepts of what type of universe. There's a lot being put into this, and what we need is evidence to show that the early energy given to us, in other words, where did matter come from? That's what you're saying, is that at our first part of the universe, and there's a typical classical answer to that, but the other outside answer to that is that where did matter come from? And was it given to us from another universe to start our universe? Okay? That's really the fundamental of that question you're saying.
But isn't the time scale for the development of stars and galaxies now?
Yep.
That's much. If we still go back to this traditional start of the universe date,
Yep.
13.7 whatever
Yep.
billion years, then we have to explain how these things happen a lot faster than we thought they did. Or did they in fact start that process before we thought that
The answer is we don't know.
Exactly.
And if I try to answer that, I'll be a fool. Okay, but these are big questions that we can't answer.
Exactly.
And you ask Brian Cox and all that, he'll say, I can't answer that question. We know 5% of what we know about the universe. I'll just run through them very quickly. So the 20 main points, what we know about the universe, and it just came out of my head one day, I typed them down. We know that the universe is that age, and it was basically born of the discovery of the cosmic microwave background by Penzance and Wilson, and we'll talk about that in a minute. It is constantly expanding, we agreed with that. It's called the cosmological constant, and then the Hubble tension comes from that particular constant. The universe is vast. If you ask astronauts or people that go into space and they look out into the darkness, the distance between things is quite incredible. If you go to the asteroid belt, they say, oh, you can't fly through the asteroid belt because you're going to hit one of these asteroids. The fact is they're millions of miles apart from each other. That's just the asteroid belt, let alone we go to the other belt on the other side of Pluto. So the distances are so big, and guess what? They're getting bigger and bigger and bigger as we sit here. Sorry? Yeah. In fact, it's said within 1 billion years, it's been calculated that when we look up to the sky, if the human race survives the next 250 years, as Stephen Hawking claimed, we won't see anything in the sky at all, because it's been going and going and going, expanding and expanding in all different directions. So there'll be nothing up there to see. Yeah, just continues to keep on. Inflation is what is generally used, the word inflation in our field. However, empty space, it always will contain a certain amount of energy. So if I took, scientifically, if I took a box, opened it up in space, a plastic box, let whatever's in that space flow into my box and then locked it down, okay, and then took it back to Earth and tested what's in that box. What do you think's in there? What's inside that sealed box?
Did you say from space?
It's not a lot. There's not a lot. However, what's in there is a huge amount of energy. There's energy there all the time. There's quantum fluctuations, these energy of particles that actually come in and out of existence. They're inside that box. But what we see is nothing in that box whatsoever, okay? But it goes further than that. In fact, the energy within space, of course, it's a set amount of energy. We know the first law of thermodynamics, meaning that you can't create it and you can't destroy it. But in fact, our energy has been diluted as our universe is getting bigger and bigger and bigger, and this jumps into how the universe will end. There's 6 different ways we know it's going to end. The main theory is that it's going to end from possibly what is known as heat death. In other words, our universe is going to expand so much that new stars will not have that energy, because remember, it's a finite amount of energy. If you're the universe and I borrow energy from you, I have to pay it back. It must be paid back at some time. So the same, if it's getting bigger and bigger, the energy that's required to make new protostars and T-Curie stars and all that requires a lot of energy. That energy will fade out to a point where it will not be able to recolonise new stars and galaxies, and the universe will just fade away and die. You've heard of the Big Rip, you've heard of the Big Ice. Einstein was pretty keen on that one, where the actual universe expanded out so far that it got so cold that stars just wouldn't ignite through the T-Curie stage. So that's what's going on with the science. There's a group of people that are looking at different versions of how the universe will end. Okay, we talked about the observable universe, these ones here. That's about what the numbers are that are used these days. How long do you reckon humans will last for?
40 years.
Anyone want to have a guess? How long will we survive in our little place on this little rock in this small solar system, in this galaxy that's smaller than Andromeda? How long are we going to last?
You don't leave about 4.5 billion years.
Yes, until the sun stops shining, and then Andromeda is going to merge with our galaxy. Yes, you're very well read.
Trump gets a third term.
Sorry?
Depends if Trump gets a third term.
That's right. Well, Stephen Hawking was quoted a year before he died in 2018, was it 18? That he gave the universe, not the universe, our Earth, human Homo sapiens, about 250 years to live. At the rate of what we're doing to ourselves, and just have a think about what's going on in the world today. We don't have to discuss it, but it's discussing what's going on. But he, just before he died, he told his daughter, revise that. It's about 1,000 years. I'll give us about 1,000 years before we annihilate ourselves. But I did a post recently in Cosmic Corner, I think a couple of months ago, what are the extinction episodes that our survival on Earth will be? Anyone know what the top one was and the second one was? What's going to kill us in the end? The asteroid hit is certainly going to be the big one. The one that came second of concern is the advance of AI. There's significant uneasiness about machines being trained and produced with AI and quantum computers coming and helping with that, that they may turn on us one day, their makers. Sorry?
No one watched Terminator?
Yeah, the Terminator. That was number 2. The other ones were climate change came down about number 5 of extinction events, because that will be a slow thing. About every 100,000 years we go through an ice age. So are we due for an ice age? Probably at some time. So that's the extinction. I'm jumping a few. Do you know what's the most, with galaxies, do you know what our black hole is inside our galaxy? Do you know what the name of our black hole is? Sagittarius A star, that's right. And it's pretty big, isn't it? Now, you know, with black holes, do you know that they actually don't suck things in? That's a fallacy. You think that black holes are like, we talked about this in our group, black holes, and Brian presented this, black holes are not a consumption vacuum of sucking galaxies in, because they can literally suck a galaxy in, destroy it. But in fact, what you have to do, if you're walking along the edge of a black hole and you're walking along the event horizon, this is where all the Hawking's radiation is coming out, and this is why black holes eventually fluff out. They don't last forever. They could last 100 billion years. It depends on their size. But in fact, if you get to the edge, you're still standing there. You're not falling in. But if you fell in, then you will fall into a black hole. You'll be spaghettified. You'll be stretched to unbelievable, atoms, and you'll flow down to what is another singularity we're talking about, said to be at the middle. And what comes out does anyone know what comes out the other end of a black hole? What the current theories are? An Italian physicist has published this only last year. Carlo Rovelli, I'll give you a heads up on that. He said white holes are at the other end of black holes. A white hole. The other theory is that there is another universe at that particular point. This is all just theoretical stuff. I think we've covered most of those. So that's what we know about the universe. One thing I'm getting involved with down where we live in Phillip Island is that the nature parks have come to us and asked us to help them with the possibility of starting an astronomy centre. Okay? And what they're currently doing is actually doing light testing of the night light along, near Seals Rocks and along there, and they're doing a very good job. And what they're trying to do at this stage is actually get the International Dark Skies Association to actually qualify them to have a precinct of dark skies where the penguins are, where they come in. And then they'll apply for that and go from there. They've never done a precinct before. The dark skies, I don't know whether you've had much to do with them, they're a very difficult mob to deal with. They aren't very cooperative and they don't hand out dark skies arenas very easily. The last one was the Tailem Bend, I think, along the Murray River heading towards Adelaide. There's a dark skies designated area there, but there's no astronomy clubs there or anything like that. You just go there and it's a dark sky. And the last one was, I thought, was Coonabarabran. Would that be right? I don't think they've given another one because basically the local council have to put in different LED lights and blinkers on their lights. So if you go to Coonabarabran, you go up to the top and see all the telescopes, you go down to the town, you'll see all the light going downwards rather than going upwards. So there's a lot of investment from the local council. But some of the information at the moment is really concerning. Recent research says that global 3 in 10 people can't see the Milky Way. That to me is unbelievable. This is, you know, big population areas, big lights here in the United States, top of Africa, all the European areas here, a little bit down there. But look at Australia, we don't even light up at all. So we have a lot of opportunities here to do what we're doing in this club and other clubs around. In the US, the number goes up. Nearly all US children live under light polluted skies. There are kids in America, about a third of the children, that will grow up and not see a star in the sky. And that bothers me like hell. I think that's just outrageous that children can't come to a club like this, look through a telescope and see Saturn and be inspired. Be inspired. That's a real problem. That's just on the side. When we talk about the Big Bang, some people have been forgotten about the Big Bang. And the father of the Big Bang, as you can see here, is Reverend George Lemaitre. Does anyone know much about him at all? He's the father of the Big Bang, okay? Now remember the Big Bang, the name from the Big Bang came from an English physicist, okay, that was doing a radio interview at the BBC in 1949. And he was being asked about the start of the universe and all that sort of stuff. And he said, oh, there was a Big Bang. And that stuck. And that's why in cosmology we use that word Big Bang. I prefer the creation theory, but it's the way it goes. So when we go back in time, the pioneers of the forefathers of cosmology was Copernicus. Everyone familiar with Copernicus? Back in the 15th century, he was lucky. He was so lucky to have people in high places because he came up with the idea that the Earth is not the centre of the universe. And remember that back then the universe is what they could see up in the heavens, not outside them. They never knew about the Milky Way at this stage, okay? So he said, oh no, you're wrong. The actual centre of the universe is this big bright star that we're going around. And Copernicus had the friends in high places that he didn't lose his head because of the church. Galileo, of course, came along and ordered his beautiful brass telescope from an optical maker in Holland, got it back, turned it up and looked at Venus and said, hang on, they called it the night star then, is actually going around the sun. Shouldn't it be going around the Earth? And then he turned his telescope to Jupiter and saw the Galilean moons rotating around Jupiter and said, but hang on, we're told that they're meant to be going around us, the Earth. Then Tycho Brahe came from a wealthy family. What happened to Tycho Brahe? He went out there and did the same thing and said, no, not what I see through a telescope. Well, they burnt him at the stake for that, for him saying, oh, going against the church. It wasn't until Kepler came along and others, and then there was a jump in maybe 200 years till we get to Newton, that the whole idea of the central concept of that the Earth is not the centre of the universe, the Sun is, really came to light. And of course, wars and all these other things that came along stopped a lot of astronomy and science from being researched. But back then, there's this guy here, Alexander Friedman. If you go back into the early 20s, this is when Planck published his papers on quantum physics, Niels Bohr and all the great Germans in the early 20s. This guy, I call him the grandfather of the Big Bang, because he actually published a paper that never got outside Russia. Papers could never be sent out. You'd have to smuggle them out, and you'd have to smuggle papers from Germany and all that into Russia to read what his colleagues were doing. And he had to work off his own information like Einstein did himself, okay? But he came up with the idea that the universe was not infinite. There was no start and all that as claimed. He actually came up with the idea of the fact that it did start from the size of an atom and then inflated out like that. Then our friend George Lemaitre, who's a Catholic priest in Belgium, early on, he trained as a lawyer originally and then became a Catholic priest, also trained as a physicist, and he taught at the local university in Belgium. And he published his paper in 1929 about the universe, taking some of his work, but actually developing the mathematics about the universe starting from a singularity and developing, coming out within a second, developing from there onwards and going out with inflation. And his paper, unfortunately, was published in a very, journal, wasn't very well known, and unfortunately it didn't get out. He chased down Einstein one day at the Copenhagen meeting and said, "Have you read my paper?" to Einstein, and Einstein stood up and said, "Yes, I have, and it's a load of rubbish." So poor George Lemaitre got knocked back. It wasn't until Edwin Hubble, everyone familiar with Hubble? Came from a very wealthy family, trained as a lawyer. His father said, "That's it, you're going to be a lawyer." Came back from England, from Harvard, and got the job. He became an astronomer too. His love was astronomy. He got the job with the 100-inch Hooker telescope up on the top. Has anyone been to the top of Los Angeles to the big telescope? Marvellous, isn't it? Well, that's where Hubble started his incredible work. And remember, these guys never got a Nobel Prize for what they did, because astronomy wasn't recognised as a Nobel Prize in those days, unfortunately. So what Hubble did was look through his telescope and he plotted all the stars going away from him. It's called blue shift. Okay, it's through spectroscopy, that's right. And this blue shift showed that the actual stars he was looking at through his telescope were actually moving away from him as the reference point. He also noticed redshift, I beg your pardon, start again. They were redshifted, moving away, but the star, or the stars within the Andromeda Galaxy, were blue shifted. And of course we know now the Andromeda Galaxy is coming towards us, and it will be here within 4.5 billion years with a lot of sparks and a lot of excitement about moving towards the Milky Way and joining our galaxy. So these guys eventually formulated the whole theory of it all. What Hubble did was actually confirm one, inflation was going on, and he confirmed the second thing, that there were more than one galaxy we all lived in. And that's a big thing. We thought the Milky Way was the only galaxy in the universe. And of course now we know there's trillions and trillions and trillions of galaxies. If you look at the deep sky photographs from Hubble and also the recent ones from James Webb, are remarkable photographs. All those little dots, they're still all galaxies. They're not stars, they're all galaxies. How exciting that is. So we have these three guys that came up with the whole theory of the Big Bang. And then we have the later guys, the contemporary guys like George Gamow, Arno Penzias and Robert Wilson. These are the guys that discovered the cosmic microwave background, Stephen Hawking, Alan Guth, Brian Greene, and there are many more cosmologists out there that actually are doing great work out there. Does anyone know what cosmology is? Can anyone describe? We know what astronomy is. Can anyone describe what astronomy is? Astronomy is a viewing of objects in the sky and the scientific study of those objects in relation to all other objects in our universe. It's a beautiful thing, whereas cosmology is a little different. However, I truly believe they're joined at the hip. Cosmology is the study of the creation of the universe all the way through to where we are now and all the way through to the end of the universe. So they are both disciplines. Cosmology actually started as a university degree in 1964 in the United States. So generally in cosmology, most people will go and do astrophysics first. If they're good at mathematics, they'll go and do that. And then they'll go and do postdoctoral research in cosmology or something like that. You've got to have a number of those talents to actually pick up this subject of cosmology if you're in the professional area of it. Okay. So the key milestones, I just call them key milestones, that sort of stuff, is our friend George Lemaitre, the father of the Big Bang. In 1927 he published his paper, and of course he didn't get a Nobel Prize for it, and he was unfortunately rejected by many of the key people. Even the key people in the quantum physics area in Germany in the great 20s rejected him too. But it took about 10 years of him working away and chipping away until they started to listen to him, and then they accepted his theory. Hubble constant, in other words, inflation of galaxies in the Milky Way, again, Hubble never got a Nobel Prize. And that's really, really sad that these guys never got a Nobel Prize. Now, the big thing, all the wars came along and interrupted science. 1964, the cosmic microwave background was discovered. Do people know the story about the cosmic microwave background? How it all came about? This is the big thing that started our understanding of the Big Bang. So when I'll briefly, no hands up. Basically what happened is the Big Bang occurred. All the heat and radiation came out, but it came out in a microwave soot or smoke coming outwards, and you can't see through it. Okay? So, I'll go on, if I may. These two guys here, Penzias and Wilson, see these two guys here? He's the older physicist and he's the younger one. You wouldn't think so because he doesn't have any hair there. But these two guys were employed by Bell Laboratories back in 1964. You're familiar with Bell Laboratories in the United States? Telephone company. They wanted to get the hiss, that static hiss, out of their telephone lines. It was driving them crazy. So they employed two physicists. They had a machine called the Big Ear, and this is made out of wood. And they spent a whole year in this little box here with instrumentation, delicate instrumentation, listening to this hiss, trying to work out what is it to start with and how do we get rid of it. This is what we've been brought in by this company to actually do. Eventually, after a year or so, they found some pigeon poo in the bottom there, inside. They jumped inside there, cleaned it out on a weekend, did a whole lot of cleaning and that, and they thought, that's it, we fixed it. Got back into the little box at the back, turned on the machine, no change whatsoever. Frustration. Couldn't be worse. So Penzias had a colleague, a collaborator colleague up north in Northern America. And he also has been thinking about this cosmic microwave background or footprint of the Big Bang. It's called the footprint. And he brought him down. He put him in the back there. And it only took one day. He came out at the end of the day, climbed down the ladder, walked up to these two guys and said, guess what you've just discovered? I said, we just don't know. He said, you just discovered the microwave background of the Big Bang, of the beginning of the universe. And that is when we all then started to know about this information that firstly, from there, from the 20s all the way through, the belief was that the universe started what they call the steady state theory. In other words, the universe had no beginning and it won't have any end, but it did expand. And Einstein put his hand up and said, I believe in that. Okay, he was one of the debutantes of the steady state. Okay, but these guys, about a year later, they went to Sweden and accepted 2 Nobel Prizes for one of the greatest scientific discoveries science has ever given, and it was done serendipitously. They didn't even know what they discovered. So from then onwards, we knew the age of the universe. So what they do is they took the speed of the universe from the Big Bang. Remember that Hubble tension we were talking about? That's speed, or velocity, probably a better word. And they took that to where we are now. So what they did is they took that velocity, turned it around and rotated it back. And we got exactly 13.79 billion years. They also studied starlight coming from new stars. There's population 1, 2 and 3 stars, and they looked at the population 3 stars of the old stars that didn't have any metal in them. They're called non-metallistic stars, okay? And they looked at those and they compared those, and they also confirmed the age of the universe itself. So we have information now that is rock solid about the starting of a universe. The only question is, one, that when did stars start? And I won't go any further, but James Webb has now shocked the world of science, saying, really, guys, we've got stars starting or even halfway through their development phase of accretion at 200 million years from the Big Bang. And in our science, that's not possible. If you look at the quantum physics side, that's not possible, okay? It normally takes about 500 million years to start that process to make a star. So we've got these new hot stars starting at that, and we've got pictures of galaxies from James Webb at 250 million years after the Big Bang. This is, well, I don't know whether you guys have been following this, but anyone that does follow this, and I'm sure you're aware of it, Peter, this is enormous news and we can't explain it, but what it's happening is that all the new trainees coming through doing astrophysics and astronomy are now having to rewrite all the textbooks. All the textbooks in science now have been rewritten because this is not experimental stuff. This is photographs from James Webb. You can't get anything better than that. There's no need to experiment that. This is evidence right in front of your face. So I'll leave it at that note. I just wanted to impress that there's such enormous change happening at the moment. So when you're looking at the stars these days, think about what type of star is it? When did it start? How long has it been there, and all that sort of stuff. And that's what we do in Cosmology. So if you want to come along to our meetings, please join us.
Are other people receiving that information to the effect that on the 15th of August, gravity is going to disappear?
Oh. Is this one a bit like I3 Atlas? You're going to ask me, is there someone inside that rock driving it? I mean, if you were Avi Loeb at Harvard University and you're in charge of the physics department and saying to the world, there's someone inside that rock going around the sun that's driving it, I beg you, what's going on in science? What's going on?
I presume everybody else is getting the same message.
Yeah, well, I've heard of it, but I haven't really had time to look at it. But yeah, if you're watching YouTube, be very careful. Very careful. We warn our people in cosmology, if you read stuff, look for the evidence. Don't just accept what's thrown in front of you. And that's what happened to I3 Atlas. And what was the other one we had called the Hawaiian name? Not the Umamamura, which is Hawaiian for visitor, isn't it? Omamura, yes. Of course. But someone told me today there's another type of YouTube, is called A YouTube or something, that's even better in lying about stuff. you know, that physicist at Harvard making statements that he thought there was someone inside that 400-metre rock flying through our solar system and going out and getting a push from the sun, there was a team of aliens in there driving it.
It sounds very similar to a science fiction a novel called Rendezvous with Rama.
Yeah,
You've read that.
Yeah. So we double, I don't know about you guys, but we really double check our information when we talk about it, and we only present what is really scientific. So thank you very much for listening. I hope it was engaging, but if you want to engage with us, come and join our meetings. We have great fun, and it's good. How would you describe it, Pram? We cover everything. Sorry?
Thought-provoking?
Thought-provoking, yes. But yes, go ahead. Final question.
Where are you based?
I'm involved with the Astronomy Club in Phillip Island, but I'm a member here also, and we run the Cosmology Group here, thanks to Peter and his help we get, and Narita and that, and we get a really good turnout up on Saturdays. But if you want to receive advance notice of what we're doing and what we're talking about, you need to be on that mail list called Cosmology East Scorpius. So you need to ring Narita, the secretary of the club, and say, can you put me on that? And we'll send you out an email. You'll also get my magazine that goes out over the world every week, called Cosmic Corner E-magazine, that goes out pretty well everywhere. And there's a lot of discussion that goes on that we talk about right from, and we go right into quantum physics and all that. We do mystify quantum physics a lot too. Thank you, everyone.
And the size of the group that comes along to the cosmology discussion meetings is about the number that are here today. So, and it's on a Saturday afternoon, usually before the working bees. It's every 6 weeks, whereas the working bees are every month.
Yeah, and we encourage. We've got Catherine McCoy. She's one of our members, and she's studying quantum physics at the moment. So she's reading a lot of the books that we suggest to read, because quantum physics is a big part of cosmology. It says what actually was there at the beginning, but she's doing a talk on women in cosmology. So, which is going to be really a nice presentation.
Clouds. They seem so simple. When they appear darker, we pack an umbrella. When they're nowhere in sight, we pack extra sunscreen. Either way, we look to clouds for more information than you might realize. But for all that they can tell us, they actually remain quite mysterious, especially when it comes to how they impact the climate. The question is, because clouds are produced by the climate, how will a changing climate impact clouds? And conversely, clouds have an impact on our climate. So how will changing clouds affect a changing climate? Welcome to Clouds 101. Like all good mysteries, this one begins with a sophisticated scientific concept, Earth's radiation budget. Earth's radiation budget describes the delicate balance between the sun's radiant energy that reaches Earth and the radiant energy that flows from Earth back out to space. About 30% of the sun's incoming energy, essentially the light and heat we're familiar with, is reflected back to space by gaseous molecules in the atmosphere, tiny particles called aerosols, land, snow and ice surfaces, and by clouds. The remaining energy from the sun, roughly 70%, is absorbed by the planet. Most of this absorbed energy heats up Earth's surface, while the rest is absorbed in the atmosphere by gas molecules, clouds, and aerosols. So heat can be both absorbed and reflected by clouds. We'll come back to this later. Heat is also separately emitted by Earth into space in the form of thermal infrared radiation, which is the kind of heat humans can only see through night vision goggles. For Earth's temperature to remain constant, the absorbed solar radiation and outgoing thermal infrared radiation must balance one another. if the Earth's system is changed either through natural phenomena like volcanic activity or through unnatural phenomena like humans burning fossil fuels, an imbalance in Earth's radiation budget occurs, and as a result, the Earth's temperature eventually increases or decreases to restore an energy balance. In recent decades, satellite and surface measurements clearly show an energy imbalance taking place that's been increasing. Over the past 150 years, the large rise in carbon dioxide emissions, which accumulate in the atmosphere, has created an enhanced greenhouse effect. This means that energy from the sun still easily reaches Earth, but Earth's thermal infrared radiation has a harder time getting out into space. This has caused a decrease in how much heat Earth sheds. Consequently, we have observed a rise in Earth's global mean surface temperature, an increased melting of snow and sea ice, sea level rise, and more extreme weather events. So that brings us back to the mystery of clouds' long-term effects on climate. Here's what we know so far. Clouds impact the radiation budget in two ways: by reflecting solar radiation back to space, which leads to a cooling effect on the climate, and by absorbing heat emitted from below the clouds that would have otherwise escaped to space if the clouds weren't present, leading to a warming effect. Which of these effects dominates in any given location depends upon the cloud type. High-altitude clouds are typically thinner and colder than low clouds, allowing for more solar radiation to pass through them and reach Earth's surface. And because they're cooler, they emit less thermal infrared radiation to space, so they have a net warming effect on the climate. Clouds at low altitudes, on the other hand, are generally thicker and reflect more solar radiation back out to space. They're also typically warmer, so they emit more thermal infrared radiation and therefore have a net cooling effect on the climate. We also know that when the climate warms, Earth can respond in ways that leads to further warming. For example, as temperatures increase, we see snowpack and sea ice melting away in polar regions, a loss of white surfaces that reflect the solar radiation. That means darker colored land and oceans left behind absorb more solar radiation, and so more heat is added to the climate system. This cycle of more heat, more melt, and more absorption of solar radiation is called a feedback cycle. And it doesn't end there. A feedback cycle also happens with clouds. Climate models predict a decrease in low-altitude cloud coverage over the globe as the climate warms. Since low clouds are the highly reflective type, a decrease in low cloud coverage means more heat will be added to the Earth's system, leading to further warming. And clouds impact the climate in another way too, through the water cycle, producing rain and snowfall. Water at Earth's surface evaporates, providing the atmosphere with a supply of water vapor. Depending on the air temperature and atmospheric pressure, the air can only hold so much water vapor until it becomes saturated. When that air saturated with water vapor cools, the water vapor turns back into liquid water droplets and forms clouds. When these droplets or ice crystals accumulate, that is what we call a cloud. When the droplets or ice crystals within the cloud grow to be large enough, they eventually fall to the ground or ocean as rain, snow, or hail. This brings us back to the mystery at hand. Because clouds both reflect and absorb energy from the sun, impacting both ends of the radiation balance, and play a massive role in the water cycle, any changes in clouds will result in a change in our climate. But clouds are also produced by our climate, so any change in climate will result in a change in clouds. As you probably now realize, the relationship between clouds and the climate is incredibly complex, and NASA is on a mission to understand it. Using NASA's Earth-observing fleet of satellites like Calypso and instruments like Ceres and MODIS, scientists have been collecting vital data on clouds to be able to precisely model their behavior. A key ingredient to unraveling the mystery of clouds lies in the collection of global, accurate, multi-decadal climate data records of cloud properties and their influence on Earth's radiation budget. Once we can accurately and fully understand the physics of clouds through observations, that data can then be used to help improve climate and weather models, so we can better prepare for the future.
Now we'll look at the moon's south pole in the areas that are permanently in shadow. This is Dr. James Green, who is NASA's chief scientist, gives this talk, goes for about 15 minutes. He was also the advisor to the Matt Damon film The Martian. And this was released a couple of years ago, so the timelines for Artemis mentioned in there are a little bit optimistic because things got a little bit delayed. And Artemis is going to land with Artemis 3 in the South Polar region.
Today I'd like to talk about the evolution of volatiles in the permanently shadowed craters in the north and south pole of the moon. Here is a lunar landscape in the South Pole, but it's taken a month for us to be able to put it together. And what we've done is shown the total month lighting conditions in the South Pole. What we see are regions that are permanently shadowed. Now these regions, of course, are impact craters that are deep, for which the sun has not been able to reach into these craters. We have realized the importance of these permanently shadowed craters holding a variety of volatiles. From orbit, our analysis seems to indicate that these may be large reservoirs of volatiles, in particular water. Now this has occurred over the history of the moon, and in addition to water, there may be other volatiles that are in these permanently shadowed regions. Since this is a region of interest for NASA and the upcoming Artemis program, we really need to understand and anticipate what kind of science that we would be able to do by getting into these permanently shadowed regions and studying the history of these volatiles that we believe are trapped there. To understand what might be available in these permanently shadowed regions, let's go back to the beginning. Let's start trying to understand how the Earth and the Moon were formed. Well, our best theory of the formation of the Earth and the Moon starts with what we call the giant impact hypothesis. Imagine 4.6 billion years ago, as our collapsing cloud is creating a disk of material that is then accumulating into these protoplanets. Around the sun in our orbit is the proto-Earth, but also other objects are accreting. We believe another object, perhaps the size of Mars, was accreting at the same time the proto-Earth was. We call that object Theia. And over time, and it's a matter of a few million years, as these objects are coming together, there's a collision between Theia and the proto-Earth. Now, upon that impact, a debris disk forms around the Earth, and it quickly coalesces to form that moon outside the Roche limit. Below the Roche limit, which is at 2.9 Earth radii, that material falls back on the Earth. But beyond the Roche limit, material can be accreted into this new object that we call the moon. Now, due to the high temperature created from this collision, it is expected that volatiles would escape this disk, leaving the resulting moon a very dry, gas-free metal poor body. So what happens over time and how the moon then could accrete more volatiles is of interest to pursue. The next concept of after the moon is formed, in that is tidal forces between the Earth and the moon are being dissipated, and as that occurs, the moon continues to move away from the Earth. In fact, the Apollo program told us, after putting retroreflectors on the moon and us bouncing lasers off these retroreflectors every year for the last 50 years, that we can see that the moon is moving away from the Earth about 1.5 inches per year. So for instance, at 3.9 billion years, some 600 or 700 million years after the Earth and Moon were formed, the Moon may be as far as 21 Earth radii away. And in fact, today, the Moon resides at about 60 Earth radii away. Well, during the time in the formation of the Moon, when the Moon was right at or near that Roche limit, it must have been enormous. We estimate that it must have been at least 16 times the size of the current Moon today. In time, over this 4.6 billion years, an event occurred called the Late Heavy Bombardment. At about 4.1 to 3.8 billion years ago, huge asteroids hit the Moon. Of course, they also hit the Earth and all the inner planets. Now, we know this occurred because we have brought back samples from the Moon and age datum. We have found the age of the Moon at the 4.6 billion years ago, but we also see these newer impacts, these newer materials are formed from impacts at the 4.1 to 3.8 billion years. Now, these impacts are from objects that are actually quite large, 100 kilometers or more in diameter. This produces huge gouging out of the crust of the Moon. In fact, the lower crust and upper mantle, which is still molten at this stage, pours into these craters, pours into what we call basins. And as it's doing so, it's also outgassing. Because this mantle material is slightly richer in metals, we then see a coloration difference between the old surface of the Moon when it was formed and this new magma that is then pouring into these basins. That color difference we can see from Earth. This is really the mare that we see in these craters on the Moon. What happens next is during the phase of magma flowing into these large basins area creating the mare, the Moon is also outgassing. So whatever volatiles are remaining within the Moon must also be percolating out. We estimate that at its peak, the atmosphere of the Moon may be as large as 10 or 12 millibars. This is even larger than the atmospheric pressure of Mars today. Now, in addition to the outgassing of the Moon from this late bombardment, the rock material that we brought back clearly indicates that the Moon also had an intrinsic magnetic field, probably generated deep in its interior through dynamo interactions. So between 4.2 and 3.2 billion years ago, then we expect the Moon to have created a magnetosphere. Now, this is significant because this magnetosphere is occurring at the same time of the Earth's magnetosphere, and also the Moon is much closer. Now, here are some basic simulations of the Earth-Moon magnetospheres. We call this a coupled set of magnetic fields. These magnetic fields, as they couple, allow atmospheric and ionospheric material flowing away from the Earth to follow these field lines and then actually be deposited on the Moon. As the outgassing occurs and the lunar atmosphere increases, we also expect some of the lunar atmosphere to flow down these field lines towards the Earth. So on the left-hand panel, when the Moon is sunward of the Earth, on the day side we see how extensive the total magnetosphere is. On the night side, the Moon is well positioned inside the tail region behind the Earth on the night side, but the field lines are still well connected, and indeed volatiles from the Earth's atmosphere must indeed be flowing onto the Moon. Well, over time, we now have recognized that, of course, the moon lost its magnetic field. It continued to move away from the Earth. The solar wind then began to strip the atmosphere, and the moon quite quickly, within about 100 million years from its peak of the magnetosphere at 4 billion years ago, then became the arid and dry moon that we see today on its surface. Now, we also have discovered most recently that micrometeors that come and impact the moon, in particular as the Earth and the Moon system move through old comet tails or old asteroid tails, debris that is flowing around the sun in these former orbits, we see these micrometeors impacting the moon, releasing subsurface water, and it's a very small amount, but it's been going on now for billions of years. And this water, of course, is going to migrate to these permanently shadowed regions. This is what we call the current water cycle on the moon. Now, in addition to H2O, to the water, we expect that and have observed other compounds trapped in the regolith, such as nitrogen, carbon, fluorine, sulfur. Perhaps all these were Earth origin, and we now understand, based on that magnetosphere of the Earth and that connection with the lunar magnetosphere, pathways for these particles and atmospheric constituents from the Earth to actually be deposited on the moon. The helium that we expect to see embedded into the lunar regolith is probably of solar origin. So, in summary then, as we return to the moon and go to the South Pole and go into these permanently shadowed regions, we would expect a stratigraphy of volatiles to be uncovered. That as we look at these cores that we would take on the moon, we would see predominant volatiles from comets and asteroids, also from the lunar atmosphere. Also, we would expect the Earth atmosphere contribution. And then, of course, water that's coming from that current water cycle of micrometeor impacts on the moon. So these cores that we expect to do, much like what we show here from systems that were developed on Earth to obtain cores at the Antarctic and the Arctic, we expect to deploy similar instruments to the moon to be able to create cores and then interrogate them, looking for these volatiles so that we can understand that overall history of the volatiles in the permanently shadowed region and the evolution of the Earth and lunar atmospheres. Now that's going to be done via the Artemis program. And the Artemis program is designed to be able to put the first woman and the next human, could be a man, could also be a woman, on the South Pole by 2024. And this requires a variety of missions to build up to that. The first one, Artemis 1, will have the Orion capsule launched by the Space Launch System, which will orbit the moon and come back, much like a figure eight that was done by early Apollo astronauts. Artemis 1 will not be crewed. Once we see all the operational systems and improve on them, then we'll send astronauts in Artemis 2 to go to that moon, figure eight orbit, and come back and return to the Earth. In the meantime, we're developing a staging area, a gateway, if you will, for which we will, with Artemis 3, dock, and then from the gateway go down to the moon and land and begin that exploration by humans. In the meantime, we will be also exploring the moon with a variety of robotic spacecraft. After Artemis 3, we have designs of increasing our participation of astronauts going to the moon for longer stays, unlike the Apollo program, for which astronauts came to the moon, stayed for a day or so, then returned. Our plan is to have a more sustainable program for which we will stay on longer time periods on the moon, from days to weeks to perhaps months, and therefore really take advantage of our scientists to study the volatiles in these permanently shadowed regions and perform a variety of experiments from the surface of the moon. We'll also be enhancing the gateway over this particular time. This is being planned with a variety of international partners. It will be led by NASA, but we anticipate many more of the space agencies will join us over time. So, what is the future exploration of the moon? Really begins with the Artemis program. We want to be able to continue to do science and exploration on the moon. We want to be able to do this in a sustainable way, live on the moon for longer periods of time, learn to work on a planetary surface. We expect to get into these permanently shadowed regions, understand the volatile history, and be able to extract a variety of things, such as the water. The water in these permanently shadowed regions, we estimate anywhere from 100 to 200 million tons of water, and that actually may be an underestimate. It's only based on our orbital knowledge, so getting down on the surface will be extremely important for us to better understand the assets that may be residing in these permanently shadowed regions. The water we can use to drink, the water we can tease apart, create rocket fuel. We also can supplement the atmosphere that we breathe with the oxygen we will extract out of the water. So indeed, we may lead into areas such as manufacturing. It turns out in the South Pole, there is a large amount of platinum group metals that we detect from orbit, and therefore there may be some important manufacturing activities that we would perform. Well, the future of the moon is bright. I hope this gives you a little indication of the exciting things that we might find. What's in those permanently shadowed regions is really going to be important to tease out, and I hope you will join us along the way. Thank you very much.
And of course, Artemis 2 is due to launch probably in the next 6 to 8 weeks. March the 6th was going to be the earliest window, I think, so they're tipping that it may be early April. So 2024 for Artemis 3 on the moon was a little bit optimistic. Okay, now we'll close with a look at the Polaris Dawn mission. And this video comes from SpaceX and the National Science Foundation. I've put it to a background music called Epic Orchestra by Alexi Action. It was launched in 2024 on a SpaceX Falcon 9 rocket, splashed down 5 days later in the Gulf of Mexico. And it's interesting that the NASA website still refers to it as the Gulf of Mexico. So they've successfully hidden that from being changed to the Gulf of America. It went up to 1,400 kilometres altitude, which is about 3 to 4 times the height of the International Space Station. And they passed through the Van Allen belt on that time as well. Basically a proof of concept, test the equipment and things that are wrong and were right. They also tried out the new spacesuits. And these spacesuits were for increased flexibility, not as much trouble with the shape of the lunar or Martian surface soil, the regolith, which is really, really nasty on the suits that Apollo wore. So they learnt a lot from the Apollo spacecraft. The 4 people on board was Commander Jared Isaacman. He's the current NASA administrator. He's the one that was initially lined up, nominated for it. Then he was thrown out of the position by the US president because he's too closely aligned with Elon Musk. And then people came to their senses and they put him back in that role. He actually privately funded the entire mission himself. Now, I don't know whether it was all his money or whether he just acted as the guarantor of it. With him was 3 others, Colonel Scott Petit, the pilot, and 2 mission specialists, Sarah Gillis and Anna Menon, who were both engineers at SpaceX at the time. And they're now also in the NASA Astronaut Corps. And interestingly, they weren't astronauts when they went up, so they're now in the Astronaut Corps learning how to be an astronaut after already having been in space. They are also, both of these women are the furthest women that have ever travelled from Earth, and they hold that record until Artemis 2 takes women around the moon in the next few weeks. So this was the first private spacewalk. It wasn't a spacewalk like we're used to seeing the Russians and the Americans doing in the 1960s and 70s. They only poked their head out the top of the spacecraft up to about waist height, holding on for dear life. Not the same, but nevertheless it would have been a thrill for them to actually do. They were both outside, only 2 of them went outside. That was Isaacman and Gillis, who's sort of shown in the top right there in that picture. They each had 7 minutes doing what they call a standing extravehicular activity. So they were basically doing calisthenics up there, testing out the motions of the spacesuits and what they could find what was good and what was wrong with them. Now, while up there, Menon, the other woman, read from her children's book, Kisses from Space, and Gillis played a violin in sync with orchestras around the world, which is the first time that they've ever played a violin in space, and they played a tune from Star Wars. Now, interestingly, this spacecraft doesn't have an airlock, so for them to actually get out of the spacecraft, they had to take all the air out and open up the whole thing to space, which meant all 4 astronauts on board had to be in their spacesuits, and they were all exposed to the vacuum of space, but only 2 of them got to stick their head out to have a look outside. Now, beforehand, to avoid getting the bends, which is known obviously from scuba divers, for example, they had to do special breathing exercises to get accustomed to a lower atmospheric pressure, and their spacesuits were pure oxygen, right? So there was no nitrogen at all. So they, over that period of 2 days, they tried to purge all nitrogen from their bloodstream. So this goes for about 2 or 3 minutes, and then we'll close.
Peter, does everybody who goes EVA, like, up at the ISS, have to do that breathing?
I do not know. In fact, it was the first time that I'd actually heard of it when I looked into this particular mission, that I hadn't heard it mentioned before. they hit at 20 kilometres an hour. So basically like a collision in your car with a brick wall at 20 kilometres an hour. If for some reason one of those chutes didn't fully unfurl, then they would have hit a little bit faster.
So with the air pressure, I think the airlock, if they had an airlock, then the pressure is decreased and increased gradually.
Well, normally a craft, if you're planning on doing this regularly, would have like a separate airlock that you would go in and out.
I don't need to do it that way because I don't have an airlock.
Well, I think it was more expedience to get it done, because even as it was, that mission was 2 years behind what they thought it was going to be.
They use the standard development.
Yeah.
The capsule which goes up to the ISS.
Exactly.
That doesn't have any lock.
Well, it does
Yeah.
when it's up. They go through
The airlock would be on the ISS side. Yeah, yeah,
That's where they
yeah.
can equalise, but I when we watched it.
Correct, yeah. They do that actually on the ISS, so not actually in that craft. So they could all say they'd been in space, it's just two of them remained strapped to their seats. All right, and with that, I'll close the meeting, and hopefully we'll see everyone with the March meeting.